In this video, we're going to derive the formula that computes the area of a parallelogram. And we're going to take for granted the axiom for area that we developed in our previous video, which is the area of a rectangle. The area of a rectangle is base times height. And we're going to base our area formula for a parallelogram on this one. In this video, we're simply going to look at the derivation of the area formula for a parallelogram. And then in the next video, we'll do a few problems putting that formula to work. So as you recall, a parallelogram has two pairs of parallel sides, as I've indicated here with these arrows. These are parallel. And the strategy for deriving the area formula for a parallelogram is quite clever. What we do is we put a straight segment down like this in the interior of the parallelogram from a corner so that it comes down and it makes a right angle here, creating a right triangle. Now, because of all the parallels here, we know these are the same length and certain angles have to be the same here. This angle matches this. There's lots of congruences here. And so this triangle right over here, we could do a triangle congruence argument. If I drop this parallel down here and extend this, that this triangle here is exactly the same as this triangle. They are congruent triangles, and so they have the same area. So I'm going to pick this triangle, and I'm going to delete it, and I'm going to move it over to this side instead. So when I do this, it creates a rectangle. So there's the parallelogram with this triangle chopped off, and I'm going to move it over to this side. So here I've created a rectangle. This is a right angle, this is a right angle, these are parallel, these are all right angles. And in making this move, I haven't altered the area of the parallelogram in any way, because I haven't gained or lost any area. So therefore, the area of this rectangle has to be the same as the area of the original parallelogram. But we know how to compute the area of a rectangle. That's our area axiom from the last lesson. It's base times height. So therefore, this parallelogram must have the same area, base times height. And so it seems like parallelograms and rectangles are the same in the way you compute their areas. It's base times height. But there's an issue here. And the issue is this. With the rectangle, the base and the height are always a pair of sides. But you can see here, if we go back, if we look at the height of this rectangle, it came from this distance right here, which is not a side of the parallelogram. It's the segment that we added in the interior that goes from base to base and is perpendicular to the two bases. And so this becomes the problem when we're dealing with parallelogram area problems, is the height of the parallelogram is not a side. It's instead the perpendicular base to base distance across from one base to the opposite base. So a couple of quick comments here on the derivation and then on how to use this formula effectively. First, couple of comments on the derivation. Sharp listeners may have noticed that I skimmed over several things that if we were doing a very careful exposition of area, I would have to justify or at least make into axioms. Like, why is it if I move this from here to here? How can I move a triangle around? Do congruent things have the same area? Can I add up these areas? A very strong and rigorous development of the area axioms would have axioms for all these things. Second concern is, what if my parallelogram were really long and skinny so that when I wanted to put in the height, it wouldn't work? What if I had some ridiculously long and skinny parallelogram? We're going to see how to deal with this with heights and things like that. But if I can't make a triangle here and just move it over because it's too long and skinny. So in this case, what I do is I put in a diagonal, and then I shift this triangle over to here. So I remove this triangle and I shift it over here so that it's not quite so long and skinny. So it looks more like this. And if now I can't fit the triangle in, I just keep repeating this. I say, okay, now I'm going to move this triangle here over to this side So I'll have, wait, does that work? You have to go the other way. But you keep moving, shifting, yeah, I have to go the other way. Now I'll shift this triangle over to here. So when I shift the triangle over to here, so here's the, I'm not going to do this one, I'm going to do this one. So I'm going to copy this across like so. And you keep moving things over until it becomes straight up and down enough so that when I put in my height, it actually fits in, and then I can shift it over and make a rectangle. And none of these moves impact the area at all. I'm just moving area around from one place to another. However, for the purpose of doing problems, the critical thing to understand, let me bring this down here, is first the area is base times height, just as it is with a rectangle. The base is always going to be one of the sides. So the base is a side of the parallelogram. And since parallelograms have opposite sides the same length, I often talk about these two things are the bases of the parallelogram because they are the same length. And then the height of the parallelogram is the perpendicular base to base distance. So this is the height. And this height does not have to be drawn so that it makes a right triangle. Because it's just simply the base to base distance. As long as it's perpendicular, I could draw it over here, I could draw it over here. You can even draw it off the edge of the parallelogram. If you extend these parallel lines that form the opposite sides, I could put a height over here. The height is simply how far apart these lines are that contain the opposite sides of the parallelogram. That is the height. So when you're solving problems, if you're given a diagram, you have to look for the perpendicular marks, and then you can use those to determine what the author of the problem is intending for the base and the height. This is a very typical sort of picture you might see. You might have, okay, let's get the area of this parallelogram, and then you have some other stuff here. And it doesn't spell out, here's the base and here's the height. But remember, the base is always a side, and the height is going to be base to base distance. So I look for the perpendicular mark. Say, okay, there's the perpendicular mark. That's going to be guiding me towards a base and a height. If I look along one direction, along one of the perpendicular lines, it should line up with the side of the parallelogram. And so this would be the base, because the base is always a side. Notice, the base is just the length of the side. It's not the length of this extension, just from there to there. And then this distance here, which goes from the base to the opposite base, must be the height. And so the area of this would be this and this multiplied together. So in the next video, we will do some problems where we have to compute the area of a parallelogram in different situations.